Okay, so my name is Alex Shames. Welcome to my presentation. It is on the physics of music, as you can clearly see. Hopefully the lamp doesn't burn out soon. And so prior to this project, I have always loved music, and I have always loved science. And for my project, I wanted to do something that combined both fields. And I knew a little bit about sound waves and things like that, but I wanted to know more. So for this project, I'm going to assume that you all have no background in science and no background in music, which is OK, because I had no background in physics at all or other than freshman physics when I began this project. The two things you need to know what an octave is, which is those are notes on the piano that have the same name, so C, C, anything like that. And you need to know the tune to Twinkle, Twinkle, Little Star. So that's it. I'm going to start by playing two chords on the piano. Here's the first one. Here's the second one. Now, I'm guessing that you all thought the first chord sounded a lot nicer. And if nice is too subjective a word for you, I would say that the first chord sounded a lot more stable. Like you could picture ending a piece or beginning a piece like this, but I don't think you could picture ending a piece or beginning a piece like this. And in fact, almost every piece does end like this, like Twinkle, Twinkle, Little Star, or Star Wars, na-na-na-na, that whole thing. And what I've found in my research, and what I'm going to try to convince you today, is that the reason the first chord sounds so much nicer is not because of your opinion or because how you've been raised or because of what society has taught us, but because of scientific and mathematical facts and scientific and mathematical truths. And to prove this, we kind of need to go all the way back and talk about what sound really is. So keep this question in mind as we go on. So the easiest way I know of to create a sound wave is like this. So what just happened when I clapped my hands? Well, I pushed my hands together, and they pushed on air molecules. And those air molecules pushed more air molecules, and those pushed more until finally they reached your ear. And the air in your ear pushed on your eardrums and made it flap back and forth. And that sends a little signal to your brain that says, oh, there's sound here. And in this diagram right here, those little circles represent air molecules. And you can see that there's areas of compression and area where there's less dense air. And those areas of compression are high pressure, and the less dense areas are low pressure. And a sound wave is that repeated pattern of the pressure. And the important thing to remember is that a sound wave isn't an entire volume of air moving. It's just a disturbance moving through the air. So the same way, if you have a slinky and push one end of the slinky, the entire slinky doesn't move. You just have that little ripple that travels through the slinky. So that's kind of what a sound wave is. So obviously, not all sound waves are the same. Humans are very good at creating sound waves, especially vocally, and we're very good at imitating sound waves. However, we're only very good at imitating certain kinds of sound waves. But what do I mean by that? So if I hum something like Twinkle, Twinkle, Little Star, it's very easy for all of you to hum that back to me. OK, pretty good. So it's very easy for you to imitate that kind of sound. But if I make a sound like this, or like that, it's very hard for you to vocally imitate that sound. So why is that? Well, here we have 4 different graphs of sound waves. And on the x-axis, we have time. And on the y-axis, we have air pressure. So since there's alternating areas of high and low pressure, when it goes up, that's high pressure, and low is low pressure. And the graphs on your, I guess it would be your left, represent sounds that are imitatable. So we have a violin, a piano, and a sine wave from a computer. So that's just a computer-generated tone. And on the left, we have the sound, or on your right, sorry, we have the sound of a door slamming. And what makes these different, you'll notice, is that they have a repeating pattern. Even though it's not all the same pattern in all of them, they do all have a repeating pattern. And that pattern is called, or the repetition of that pattern, the number of times that pattern repeats every second is called the frequency. So if it has a frequency, if it happens 6 times every second, you would say it has a frequency of 6 hertz is the unit we use. And that frequency is what makes pitches imitatable. So that when that frequency pushes on your eardrums, it makes your eardrums vibrate in a very, very regular way. And it's easy for you to command your vocal cords to vibrate in that same way. The pitch on your right, sorry, backwards for me, doesn't really have any repeating pattern. And it's much harder to imitate that sound with your voice. I'm sure some people can do it, but not everyone can do it easily. And another way, this imitatability, this imitableness quality is the word pitch. That's what we mean when we say a sound has a pitch. It means we can imitate it. It means it has this repeating pattern. So one thing to keep in mind, the second question we're going to ask is the pitches on the notes on the left. Even though they all have the same frequency, they all have a pattern that repeats the same number of times every second, they look very different. And if you heard those notes being played by a piano, a violin, and a computer, they would be the same pitch, but they would all sound different. So one other question we're going to try and answer is why do they all sound different even though it's the same note? And a kind of sub-question of that is why, when I'm talking, can you tell it's my voice instead of someone else's voice? And to answer that question, as well as our initial question, we have to look at how sound waves are created. Now, a very common way to create sound is with a string, like on a violin, making a string vibrate. But we're going to use a little metaphor, like a rocking chair. Now, when you push someone on a rocking chair, it takes the chair a certain number of times, a certain amount of time to rock back and forth. And if you push the chair at the correct time, when it's rocking towards you, if you push it at that time, every time, it will keep rocking harder and harder on its own. You don't have to keep applying more and more force. It'll just keep going. And if you push the chair too often, if you push it when it's away from you, then you'll damper it and it won't rock. If you don't push it often enough, it won't pick up enough speed and it won't rock at all. So there's a certain kind of Goldilocks frequency, a certain number of rocks per second that it likes to rock at. And if you push it at this frequency, the chair will just continue rocking on its own. And remarkably, the same thing can be said for a piece of string. That string has a certain frequency that it likes to vibrate at. It's called a resonant frequency. And if you pluck a string, no matter where you pluck it, no matter how hard you pluck it, it will vibrate at that frequency. If any of you play violin, which I don't know if you do, but you know that if you play pizzicato, you just pluck the string. You don't have to pluck it at a certain spot or pluck it at a certain angle. It just vibrates at the correct frequency. And when you push a rocking chair, instead of pushing it every time it comes back to you, you could also push it every other time, or every third time, or every fourth time, and it would still gain speed, though not as quickly. And the same can be said of a string. If you push it at its resonant frequency, it will still vibrate. If you push it at twice its resonant frequency, it will still vibrate. If you push it at 3 times its resonant frequency. And I have a cool video that I can show you that demonstrates this very well. I'll pull this up right now. Turn the sound off. But this woman has a string, and she has a little shaker. Whoop. I'll turn the sound off. She has a shaker on the end of the string that will shake the string in a certain number of times per second. And initially, it won't look like anything is happening, but the shaker is on. It's just not shaking the string at its resonant frequency. And watch what happens when she gets to the resonant frequency. You'll know it when you see it. So right now, it's not at the resonant frequency. She's turning it up, and when it gets to about 40 shakes per second, you'll notice something very interesting happening. Just like that. So that's what happens when you move things at their preferred frequency. So let's say you had 2 strings next to each other, and they have the same resonant frequency. If you pluck one, it'll start vibrating at its resonant frequency, and it'll push the air around it at its resonant frequency, and that air will move and push the other string at its resonant frequency. So that other string will start to vibrate. So if you have 2 strings next to each other that have the same frequency, and pluck one, the other one will start vibrating all by itself. No matter, you don't need to do anything to it. And remember, talking about how strings, even if they're hit at double their frequency or 3 times their frequency, they'll still start to vibrate. So if you pluck a string and there's a string next to it with double the frequency, it'll start to vibrate all by itself. You don't have to do anything. And this fact is very remarkable because 2 strings that our frequencies differ by a factor of 2 are an octave apart. So we have that fact, as it might seem kind of unremarkable, but it's very important because that is how people first discovered the octave and first discovered the musical interval. And that is why cultures that develop music completely independently of each other all acknowledge octaves. There are some things in music that are different, but octaves are the same across the board. And when you think about cultures develop religion and language and art, those can be completely different, but octaves are all there. And that's because of this mathematical and scientific facts that octaves are based in. So now that we know that doubling the frequency makes the pitch go up an octave, hypothetically could see what happens when we triple, quadruple, or quintuple the frequency, but luckily I have already done that for us. It's called the Overtone Series, and anytime you play a pitch, it has these overtones in that pitch. You can't always hear them all, but they're there, and I can actually demonstrate this for you right now. So we're going to start with this note, and the first overtone is this note. So what I'm going to do is I'm going to hold this down, hold it down so it doesn't make a sound, and I'm going to play that first note, and you will hear this pitch. You will hear this pitch vibrating. I'm not doing anything. I'm not playing it. It's just going to start vibrating by itself. And you can go on to the next overtone, that one, and to the next one. The next one is this. That's the next one. Might be a little quiet. This is the next one. Sometimes they're too hard to hear. It's quiet. But you could hear the first ones. They're all there. And So any pitch has all those overtones in it, but the pitches differ in how much of each overtone they have. So some pitches might have a lot of the first overtone and not a lot of the other ones, or a lot of the second overtone and not a lot of the other ones. And if we return to our second question, why do the piano and the violin sound different on the same pitch? That's because they have differing amount of overtones. So violins have a lot of overtones. That's why the violin wave was very squiggly. Pianos have less, so it's much more like the sine wave. Flutes have even less, so a flute wave is almost just like the sine wave. And very nasally instruments like an oboe or a clarinet have a ton of overtones, so their sine waves are all messed up. And overtones are also the reason why language can exist, because they're spoken language at least. Because when I'm talking or when anyone is talking, the reason you can understand me is because I'm moving my lips and my tongue, and that changes the overtones in my voice, and you can understand words I'm saying. That's why we cannot have spoken language without overtones. And overtones also give us a way to answer our first question about why the first chord sounded so much nicer than the second chord. Because when we have overtones and we can start classifying sounds based on their frequency, we can start classifying them based on frequency ratios. So octaves, when you double the frequency, have a frequency ratio of 2 to 1, because one of them is double the other. And 2 to 1 is pretty much the simplest interval you can have, other than 1 to 1, but that doesn't really count as an interval. And octaves are also considered the most stable interval. Like, this doesn't have to go anywhere. You can hardly even tell it's an interval. You could end a piece with this, you could begin a piece with that, anything. The first chord I played is a perfect fifth. You'll see a perfect fifth is the first interval besides an octave you get in the Overtone series. And perfect fifths have a ratio of 3 to 2, which is the next simplest ratio. Perfect fifths are very stable. It's the second interval people discovered because Pythagoras back in the day was playing around with string, and he said you pluck a string and you get a pitch, cut it in half, you get a second pitch, cut it in thirds, you get a pitch, a perfect fifth above. So perfect fifths were the second interval discovered, and they have a ratio of 3 to 2, which is a very simple ratio. The second chord I played was this. It's called a tritone. It's also known as the devil's interval. That has a ratio of 7 to 5. Not a very simple ratio, not very nice. If your eardrum is flapping 7 times over 5 times, it's very hard for your brain to make sense of that. Not very nice. Maybe some of you thought it sounded nice if you like weird things, but I don't think any of you did. So this way of classifying chords based on their frequency ratios gives us a method to understand why some sounds are better than others. Because simple ratios make sense. They're easy for our brain to make sense of. Our ears can make sense of them. They make sense. And so this is the kind of mathematical basis for all of music. And my prediction is that if all of civilization died out tomorrow and we had to rebuild everything from scratch, almost everything would turn out different. Government would be different, religion would be different, language would be different. But very few things, science would eventually be different would eventually be the same, once we caught up. And I'm willing to bet that music would be the same, because music isn't something we kind of invent. These intervals are things we discover. They exist whether or not we exist. A string will always go up an octave if you cut it in half, no matter if humans exist or not. And that's because music has this truth to it that a lot of other things don't have. It can be an art, but you can also think of it as a science. So there are 2 more things I want to talk about before ending. One of them is did it just die? Okay, winging it now. One of them is my project. So the element hydrogen emits light at specific frequencies, and only these frequencies. You don't need to know why. I don't really know why myself, but you just need to know that it emits light at these frequencies. And there's an equation, which would be projected up there, that you can use to predict these frequencies. Yeah, I can write it out. It's called the Rydberg or the Rydberg Equation, and it looks something like this. This represents the frequency of the light wave. R is just a constant. And these ends, I think I'm writing this right. Yeah, these ends just represent states that electrons can exist in. So this equation gives you light waves. And what I was thinking from our project is, what would happen if instead of light waves, you got sound waves? So I had to mess around with the equation a little. Instead of, whoops, forgot the close parenthesis. Instead of R, I changed it to 440. Because 440 is the pitch of A, this A right here in the piano. It's called A440. That's the note orchestras tune to. So this will give us, if you use this equation, plug in values for N1 and N2, you will get frequency values for notes. And you get this sequence. If I played around with the values a little, you get this sequence of notes. Which isn't very pretty in and of itself, but after some muddling and after adding harmonies and things, it sounds very nice. There will be a recording of that song that I composed on my website shortly. We had to work out we were getting a keyboard for the recording studio, but things got messed up and it got delivered late. But that will be on my website soon. And so the last thing I want to talk about, which isn't as related to the physics of music, but it is related to my project. And I do think if any of my project can be considered the most important part, I think it's this part. So most people, when I told them about my project, said something like, wow, that sounds really, really cool. Good luck. That's awesome, which was great to hear. But some people said something like, wow, that sounds really cool, but I feel like you're kind of ruining music. Like you're taking music, which is great, and you're turning it into boring equations and graphs. And my response to that is, yes, I am turning music into equations and graphs, but that doesn't ruin music. For me, it makes the music more interesting, because now when I listen to music, I can enjoy the sound of the music, and I can also enjoy knowing why it sounds the way it does, and why it was written the way it does, and how I'm hearing that music, and why those chords sound good or why those chords sound bad. And I would have up there projected a quote by Richard Feynman, which I unfortunately do not have memorized, so I can't say it for you, but it's something like this. Someone asked him, I feel like you're ruining the beauty of a flower when you're turning it into all these physics and color equations and everything. And he said, yes, but that doesn't subtract from the beauty. It only adds to the beauty. And so I want to sum up my project by saying that knowing all this about music doesn't subtract from the music. It only adds to the music. And I hope that after watching my presentation, it adds to the music for you. So thank you very much. Now open it for questions. Yes?
Did you have an opportunity to analyze a piece of work by a musician?
I didn't officially sit down and be like, I'm going to analyze this, but I did look at some kind of specific chords and specific notes that are very common and see what the frequency ratios look like. In general, chords at the ends of pieces like this have very simple ratios like this. That's 5 to 3, and that's 3 to 5, and that's 2 to 1. Chords in the middle of pieces like what is it? That's usually when the piece is the second to last chord. That's the tritone right there with the ugly ratio of 7 to 5. So they do show up in a lot of music. Any other questions? Yes?
Did you start composing music before you did this?
Have
you ever done that?
Never have. This was the first time. I was hoping it turned out well, and it did, luckily. But I was just kind of jumping into the deep end with that. Yes, you had a question? Yeah?
How did you come to this?
I watched a couple, I think it was last year, I watched a YouTube video called The Sound of Hydrogen. And what this guy did is he took that equation and plugged it into Mathematica and said, here's what it would sound like. It wasn't a song, but it was just a ooh kind of pitch. It was a very ethereal, eerie sound. And I thought, that's really cool, but one sound isn't that impressive. So I thought, okay, maybe I could make a whole bunch of sounds. And then I tried doing that, and I was like, okay, well, I need to understand more about sound waves and acoustics and everything before that. And then it kind of turned into this. Yes?
So at the beginning, you also mentioned a little bit about the human voice
Mm-hmm.
as an instrument, or
Mm-hmm.
can you say a little bit more about what you learned about that?
Well, humans were very good at creating sound waves. We're very good vocally at creating sound waves, but we're very limited in the sense that we can only intentionally create pitches that are easy to create, like singing la. It's very easy for my vocal cords to go back and forth at an even number of times. But things like the door slamming are very, very hard to imitate for us. So what makes the human voice kind of special is that we can make those pitches. We can make pitches other than random sounds. I'm going to make pitches right now. These are just sounds, but we can also make pitches. But it's very hard to make intentional non-pitches, if that makes sense. Yes?
My question is somewhat related to Drake's, and I'm going to talk through it.
Okay.
I don't quite understand the question.
Okay.
I'm hoping that you can shed some light on this. So you talk about how certain tones, certain waves are lower, certain waves are higher, and you can change those things, right? So you can change them by understanding the ratio and moving them up.
What do you mean? What do you mean by change them?
Changing them in the sense that you recognize certain ratio patterns, and so if you want to understand the ratio patterns, you can make different ratios make different
Oh yeah.
sounds, right? So if we're applying this to human voice, is it possible that someone who, for instance, has a baritone or a bass or a very low octave sound, that by understanding
a good question.
You're actually not talking more like Alex, but you can talk like someone.
Like, hello, like that.
Could you change that and make that?
That is a really good question. The answer, unfortunately, is no. I wish the answer was yes, maybe in the future. But the reason, the same way on a piece of string, if you pull it tighter and tighter, you can get higher and higher noises, but you can't go all the way higher. It's the same thing with our vocal cords. They can flap faster and faster and faster, but some people have very thick vocal cords, like a deep bass will have thick vocal cords, and they max out at a certain speed. People with higher voices have thinner vocal cords, and they can flap faster and faster and faster. Maybe someday there'll be some kind of surgery you can get on your vocal cords to thin them out, but for now, unfortunately, I think you're stuck as a bass if you're a bass. Yes?
So I love what you did with overtone.
Oh, thank you.
I'm wondering, I know that in a chorus you also get overtones, but a lot of people are together.
It could just be that they're doubling up on voices. If someone's singing down here, they might also have someone sing up there. But overtones mostly happen in your ear because the way your ear works is you have this membrane that gradually gets tighter and tighter as you go down. So if you have a sound wave coming in, it'll hit the certain part of the membrane that vibrates at its frequency, but it'll also hit twice the frequency every other time. So if someone's singing a note, it'll hit that part of your ear and hit the next part and hit the next part. So in a chorus, it's the same as with anything else. It's all in your ears pretty much.
You make it look all so easy. What was the most challenging thing for you?
The most challenging thing was finding sources that weren't all exactly the same. Because I was trying to create this complete picture, and a lot of the sources were, here's this book devoted to the Overtone Series. Here's another book devoted to the Overtone Series. And everything was repetition of the other things. So I would get really excited that I found one other source, then it would just be a summary of everything else. So I did a lot of digging, and I found enough to make this complete picture. But I think that was the most challenging part. Anything else? Yes?
You did the formula,
Mm-hmm.
the Rydberg.
Yep.
You took it from sound.
Mm-hmm.
Did you come up with the idea between the 440 there? Right?
No, that was something I actually took from that original video. But you could do that with any number. I just picked 440 because it's a pitch people know. Like A440, you probably have heard that somewhere. It's also right in the middle of the piano, so I wouldn't get notes that were way up there or way down there.
String has a different
Yeah, each string has a different vibration frequency. A440 is what they all tune to. It's what violins tune to as well. And originally, if you used R, the original number that was there, R is I can't remember if it's very small or very big, but it's a very extreme number. So you would get huge or tiny frequency values, so you have to change that in order to kind of shift it into the audible spectrum. Thank you. Yes? I can, if you would like, yeah. We can leave it here, it's fine, yeah. We'll just keep it overnight. I'll move the chair, yeah. So the original tune I ended up with was, the original tune is, and then to make it sound a little nicer, I added a couple notes in, so it's, oh, sorry, I messed up. All right, let me start over. There we go. So that's the adjusted tune, and then this is it with all the harmonies and everything. Just roll up my sleeves, 1 second. Ugh. This chair is a little low. Can everyone hear this back there? So it goes something like... the recording of that will hopefully be up soon. We have to work out getting the piano keyboard into the library. Any other questions? No? Oh, yes.
The future of the project.
Future of the project, hopefully making more songs like that. I have a couple ideas. Other elements would be difficult, but I have a couple ideas, maybe waves of earthquakes I think would be very cool to turn into sound waves. Other elements, I was thinking of doing a complete chemical reaction. Yes, did you have a question?
No, it was something random.
Oh, okay. Yeah, I think it would be very cool to do like the reaction of photosynthesis, turn that into song, see what that would sound like. Anything else?
Going on to college.
Yes.
And what are you going to major in?
I am probably either biology or math, one of those two things. I will definitely keep doing music. I don't think I'm going to be a music major, but something like that. Anything else?
Where are you going to school?
Wesleyan University in Connecticut. Anything else?
Do your friends or family members have any reactions to being with you when you're creating music, or?
They're not usually there. My parents sometimes, if it's late at night, tell me to be quiet. But I think they like it in general. Yeah, I think they liked it. They didn't really give me too much feedback, but I think they liked it. Yeah. Sam, do you have any thoughts? Did you like it? We have a real live family member here.
He's being nice. Come on, Sam.
Did it affect your, I was listening to music at all?
Yeah, he was at college. He didn't hear it, so. Mhm.
Yeah, I think it would be great if you were working in the music department here.
It would be great too.
Collaboration.
Anything else? Last question. Was that it? Great. Thank you very much.